Yo, what's cracking, mates? I'm finally back and ready to erode once more any standards you might hold for good taste and decency. As a little gift to conclude this year, I continue the Pokémon glitch fixing series. It's been quite some time, bet you didn't see that one coming. Let's see what's on the menu today. Here we go, that looks kinda niche and interesting, and it's something technical once again. Clench all four of your cheeks, my big bouncy babies. We are going to analyze ARM 7 assembly once again. Like in my video about the toxic catch rate glitch, I take a shortcut by having a look at the Ruby decompilation project. I know, it's a little bit like cheating, but I think I still would be able to pull it off, just way slower. There is already a ton of things on my plate right now, and I honestly don't want to lose too much time with a single project. After a little bit of digging through the source files, I found this particular line. It's commented out as I can see, and the line above explains what it is all about, even though this is only half the truth. More on that later. 1936 would apply the inverted bit mask of the Nightmare flag to status 2 in order to clear it. For those uninitiated, during battle the status data of party members is copied into a new section of memory. Permanent ailments go into status 1, whereas the volatile ones are in status 2. Looking at the struct definition of cheap battlemons, we can see that both status 1 and status 2 are 32-bit values, which are right next to each other. Let's move on to find some landmarks in the code right before 1936, where we know the translated assembly to. The checks for the status conditions are a perfect example. We just have to look up the bit masks, and they should be easy enough to find, since they stick out of the rest of the assembly. Here are those masks, and also in the order they appear in. 88 for both toxic and poison, 07 is sleep, 40 means paralyzed, burn uses 10, and last but not least we have 40 for freeze. Now we just need to find the nearest assembly entry point, which is as close to our desired target as possible. For that, we scroll upwards and find the name of the function we currently reside in. 1734 says it's called Ability Battle Effects. Now let's go to the root of this repo and switch the branch to symbols. There is a unique file for each version of the ROM, which contains the addresses of variables, functions and so on. In my case, it's the English European revision 1. We open that symbol file, click on View Raw and look up the function entry. According to that file, the offset is 8018324 hex. Please remember that this is the offset from the point of view of the GBA processor. In order to find the offset inside the ROM file on the disk later, it's necessary to subtract an offset. Let's load the ROM in the no cache GBA debugger version and jump right to the offset we just found out. It's a push statement, which is indicative of a function start. Seems we didn't make any major investigation mistakes. Either go down the instructions manually from here until you hit your desired landmarks, or just use the search string function. In my case, I search for 88H, so I land on the next instruction using the value for the toxic and poison bit mask. And sure enough, if we scroll down a little bit further, we can already see all other subsequent bit mask checks. Address 8018960 hex is where status 1 is reset. It writes R4's content to the memory offset stored in R5. This one, of course, I only know through debugging. I can't know that by just looking at the instruction. In order to keep the video from becoming way too long, as well as making it easier to watch and understand, I'll do the rest in a split screen view. On the left side is the section of instructions from the original Ruby ROM, and on the right side my fixed version. Deleted instructions will be shaded red when I talk about them. Blue is for those where I transformed them into another instruction doing basically the same thing, and green is for added instructions. Mind you that after all, we still have to get the same amount of bytes after our fix as we started with. Also take into account that fixing this took an absolute assembly noob like me pretty much 2 days of reverse engineering, trying to understand and failing horribly. I'll do my best to emulate the thought process ahead in order to arrive at the solution I came up with. And of course, there are other solutions too. After all, alle Wege führen nach Rom, but I try to keep as much of the original code as possible. If there are smarter ways to solve the problem, by all means tell me about it, I'm always eager to improve. The first course of action is generating instructions for clearing status 2. We have to fetch the affected memory into a register since the GBA's processor can't work on RAM directly. As we have figured out before, both status 1 and 2 are 4-byte values each and lie next to each other. The flag for Nightmare is stored in the most significant byte of status 2, but since the processor operates in Big Endian mode, it's actually stored in the very last byte of this 8-byte sequence. Thankfully, we can just reuse the R5 register, which already stores the address of status 1, and simply add an offset. The reason why I only load a single byte into the register instead of all 4 bytes is that I can keep the following move instruction a small 2-byte thumb instruction too, since I only have to encode a small value. Now the reversed Nightmare bit mask is applied to the byte we just loaded, and in the end this byte is stored back at the same offset we loaded it from. The chosen registers R0 and R4 are not coincidences either. They are all written right afterwards by load register instructions, so I can rest assured that I don't screw with the game's logic by reusing them right here. In total, these are 4 new thumb instructions, 2 bytes each, and in order for them to fit neatly into the ROM, we have to get rid of 8 bytes before. By using the same trick as in the toxic catch rate video, we can easily achieve this. The compare after the bit masks have been applied via AND are functionally redundant, since the AND instruction with the yes flag already sets the 0 register needed for the branch if equal. You probably already noticed by now that this wasn't the only change I had to make. The way the load register instructions for R0 and R1 have been called here uses an offset to their address, which more or less only works in 4-byte steps. Since we shifted the instructions position by deleting the compares before, they no longer align in the way to access the necessary addresses. To make those work again, they have to be rearranged at certain offsets so the alignment matches. In order to pull that off, we need a little bit more space, and thankfully I have one more trick up my sleeve. It's actually unnecessary to repeatedly load status 2 into R0 for each check. I only do that for the toxic and poison check at the very beginning and subsequently use the test instruction instead of the end. That instruction applies the bit mask and sets the status registers without overriding the target register R0, so I don't have to reload every time. With the space we just gained, we can move the load register instruction for R1 upwards. It's of course pretty much useless to load a value into the register if we potentially jump right to the next check, but at least the data is aligned now. In addition, we can do that because the load register instruction does not touch the status registers at all, so they still will have the values set by test. Since we no longer reload R0 for every check and it is overwritten in the code referenced by the branch link, which is actually responsible for printing the Shedskin queue message, we have to jump right to the clearing of status 1 afterwards. But because we have more than enough space now anyway, this isn't an issue at all. The last block for the freeze condition doesn't have a branch, but is rather padded with a no-op, since it isn't necessary anyway. And we're done. The logic works as intended now. If you are asking yourself why I chose to go the hard route of doing the corrections in assembly instead of just uncommenting the line and compiling the ROM, I do it because I can. It's also a challenge to pull it off through the restrictions set in place, and it's way more interesting to learn assembly that way. Also keep in mind that this way, the offsets of all the instructions before and after our fix are kept exactly the same. This means any binary patches written for those ROMs can still be used without any issues. And by the way, if you remember about the comment from the decompilation, this bug actually has already been fixed in FireRed and LeafGreen, which have been released before Emerald. Interestingly enough, they aren't only clearing the nightmare from Status 2 in the Shed Skin code, but they also do another failsafe check in the Nightmare code. And that concludes today's lesson. I hope it was interesting. And since there is only very little time left, I already wish you a good start into 2023. It's going to be a banger, believe me. Smell ya later.